Good evening. Now we are going to be with third video, that is on IS 456 clauses. So now we are to the next. So we are going, that is one by one clauses. If anything missing, please inform. So IS 456 2000 plain and reinforced concrete code of practice beam. Now we have seen already what is effective depth clause number 23. We have to keep in mind, and they have mentioned there effective depth of a beam is the distance clearly mentioned between the centroid of the area of tension reinforcement and the maximum compression fiber, excluding the thickness of finishing material, not placed monolithically with the member, and thickness of any concrete provided to allow for wear. So we have simply center of reinforcement, centroid they are mentioning. So we have like this, and in this position neutral axis. So this part is compression, tension. So compression we have, that is, and the maximum compression fiber. So we have topmost fiber to the centroid of the reinforcement, to the center of this. And then we have this value as D, effective depth. This will not apply to deep beams. We are not interested with deep beams. Then T and L beam, a slab which is assumed to act as a compression flange. So that is most important. A slab. So here you can see this slab which is assumed to act as a compression flange. That means my slab should be on compression side. Then only we are going to say that beam is T beam or that beam is L beam. If slab is not on compression side, then that beam will not be considered as T or L beam. And therefore at support, our tension is at top. At support, tension at top, and therefore slab is in tension. Slab is on tension side, and therefore it will not act as T beam, and that beam will be rectangular beam. So second criteria they have mentioned here, transfer reinforcement of flange of T beam. So we have transfer reinforcement of flange. So clearly read this. Transverse reinforcement in flange of T beam when main reinforcement of slab is parallel to the beam. So when main reinforcement parallel to beams, span of beam, then again my beam acts as rectangular beam. Beam acts as rectangular beam. So to make it as T beam, they have given condition. So first condition we have actually, the slab should cast integrally with the web, or the web and slab shall be effectively bonded together. Anyway, then second, this is if main reinforcement of slab is parallel to the beam, then what we have to do to make or to work that beam as T beam, you have to provide transverse reinforcement greater than 60% of main reinforcement. So that transfer reinforcement shall not be less than 60%. Means we have to provide transverse reinforcement greater than 60% of main reinforcement. Then again, beam acts as T beam. Beam acts as T or L beam, though main reinforcement parallel to beam. Main reinforcement parallel to span of beam or beam. So if this condition is not satisfied, then I have mentioned over here, beam will act as rectangular beam. So this is most important clause, and this clause is generally asked, that is in orals. That is how we will decide the beam, given beam is T beam or L beam. And we have clause number 23.1. These all clauses are given on page number 36. Then we have 23.1.2, and this we have, that is effective width of flange. So once we have decided that our beam, that is T beam or L beam, then we have for T beam L0 by 6 plus BW plus 6 DL. So we have to little bit keep in mind. So when we have this as T beam, so to keep in mind, so we have both, that is 6, 6. So we have L0 by 6. We have same, and therefore these factors are same, 6, 6. So L0 by 6 plus BW plus 6 DF. That is for T beam. And then for L beam, we have 12 and 3. So we have 12, 3s are 36, 6 are 36. In T beam, we can keep in mind, both flanges are same. So we have these values as 6, 6. What is L0? This is most important. This is span, or we can say distance between zero bending moment. So now if we have this as beam, we will draw bending moment diagram. Then we are being bending moment diagram in this fashion. So we have top, sorry. So actually we have, this will be 0. We have top, that is hogging bending moment. So this part is tension, this part is in tension, and here we have this part is in compression. What is L0? So distance between zero bending moment. So we have, this will be L0. You should be in position to show value of L0 for a continuous beam. Then we have for isolated beam. Now we have seen this, that is when we are with slab beam type footing. And in slab beam type footing, our beam is acting as isolated inverted beam. So isolated inverted beam. And there we are going to use inverted, I can say T beam. And there we have to use this value, that is L0 upon L0 by B plus 4 plus BW. And we have seen how we will calculate L0. So that is zero bend distance between zero bending moment. And that already one problem we have solved over there. L beam, that actually we are not being with this L beam in our syllabus. So we have formula in this fashion, 0.5 L0, L0 by B plus B. So change we have just, this will be 0.5. So these are on page number 37. Then we can have the vertical deflection. Now this is for slab also and for beam also. So first we have up to 10 meter. We have these three values. 7 for cantilever, 20 simply supported, 26 we have for continuous. Now if span is more than 10 meter, the values in A may be multiplied by 10 by span. So we are going to multiply 10 by span. But when our value of span that is greater than 10, and that in this case, your question you may have that if my span is 12 meter, in that case, these values will be increased or decreased. So when your span goes more than 10 meter, so you have to multiply it by 10 by span. So if you multiply it by 10 by 12, then automatically your value is going to be reduced, because this factor you have at most 1 if both are equal. And for that we have 7, 20 and 26. And when it is greater than 10, then this factor will be less than 1 and your values will be reduced. So for span greater than 10 meter, these values are less than 7, 20 and 26. Then we have, depending upon the area and stress of steel for tension reinforcement, So this graph is given, that is on page number 37, figure 4. And we have to multiply with these values. That depends upon your grade of steel. So now you can see we have given this formula 0.58 Fy, and we are in first because we do not know area of steel and steel provided. So this value we are going to assume 1, and then this becomes 0.58 Fy. And accordingly, we are going to get these values. So if we will go, that is 0.58 into Fy. And if we will consider 250, then we will have this value, that is 250. So we have this value 145. So you may ask, so this curve we are going to use, that is for Fe 250. Then second, we have, that is 415 into 0.58. We have 240.7. So we have this curve we are going to use for Fe 415. And last curve, that is 290. We are going to use, that is for Fe 500. So likewise, we have to use these curves to consider modification factor, and by this modification factor we are going to increase this value, that is basic value of effective depth ratio to span. Then we have, so this graph is on page number 37, and this A, B, C, these are given on page number 37. So last one, that is compression reinforcement. The values of span to depth ratio, that is given actually on same page, but we are not using that one. So we are using graph figure number 4 only. And now that is percentage reinforcement and modification factor. You can see if your percentage reinforcement go on increasing, then your modification factor that decreases. So we have to keep in mind, and if modification factor we have decreases, so automatically our depth requirement is increases. You can see we have L by D, if I will say it is 20. Now, if we will have this, D is equal to L by 20, and this is into modification factor. So we have L upon 20 into modification factor. So if modification factor is larger, then we have depth required is lesser. And if it is lesser, then depth required is smaller. But generally, we have this reinforcement that we are considering up to 1%. We are not going much more than that when. So we are going to be values of modification factor is generally considered as 1.4. So we are considering 1.4, and then we are solving the problems. If our Fe 500, so you can go little bit less, also 1.2, and likewise. Then we have second this clause when we have this two-way slabs, and for two-way slabs we can use this up to 3.5 meters with mild steel reinforcement. Then slab to depth ratios are generally as given below, but we have two restrictions: span up to 3.5 meter and deflection limits for loading class up to 3, means we have that is live load, that value we have up to 3, and value simply supported 35, and continuous we have 40. So now we can use this value for Fe 415 and Fe 500, but we are generally with this one, and so if multiplied by 0.8, then we are going to get 8 5s of 40, 28. And if you will see, we have that is simply supported over there 20, and modification factor we are generally using 1.4. So this value comes around 28. So not much change. We will use that values and we will use these values. So are very close answers. We are very close for both. Here also you can have 0.8, and then it comes 32. And there we have 26. And if we will have 1.4, 8, 34.4. So that is again on higher side. So we are being likewise. So values are very close. So not much difference. And this we are assuming actually. So now we have next loads on supporting beams. And that we have one way and two ways here differently. So now you can see this. Already you are with this presentation. I will go very fast. Load from slab to beam. One way slab. So in case of one way slab, load is taken by long beams, half on two long beams. So short beams are not any load. Short beams don't have load due to slab. Load due to slab, but that is in one way slab. One way slab, total load is transferred to long span beams. So you can see this. So we are being B1 half of this, B2 half of from both sides, and then we have B3 half on this side. So I will not go much in detail. So we are being in this way. So half up from both sides here, you can see this load transfer. So Lx1 by 2 and Lx2 by 2. And this will be load on beam B2. Now load on supporting beams in case of two-way slabs, so angle we have 45 degrees and therefore we have whatever this, so that will be Lx by 2 because we have this total that is Lx. So when we will have perpendicular from this, so this becomes Lx by 2, this becomes Lx by 2. And half, as we have this one angle is 45 degrees, so we have this half span and height should be same. And in this way, we are going to transfer load. So triangular load on shorter span and trapezoidal load on longer span. So I will just go very fast so you can have with this. And then I will show that is on two-way slab. So I will go a little bit fast. Equivalent UDL. We have taken total load, calculated reaction. Due to this reaction, we have calculated bending moment at center. And that bending moment, we are going to equate. So with UDL, equivalent UDL, and then we are going to be value. W equivalent is WLX by 3. That is for shorter span when we have load that is triangular load. So this value we should know. And this is for bending moment. If we will go for shear, then half up and then we will equate it. And then we have W equivalent, that is WLX by 2. That is for your shear. So for bending moment, WLX by 3. And for shear, we have WLX by 4. Now, if we will go trapezoidal in the same way, we have to find first reactions. Total load we have calculated, half of reaction on both sides. So after reaction, we have to find bending moment at center. So we have calculated bending moment at mid-span. And we have this value bending moment at mid-span. And then that value of bending moment at mid-span, we have equated with equivalent. So W equivalent L square by 8. And then from this, we are going to get this beta Ly by Lx. So now here we have to keep in mind, this is Ly square. And then we are converting it into Lx. So we have W equivalent equal to WLX by 2 in bracket 1 minus 1 upon 3 beta square. So little bit you can keep in mind, we have in triangular WLX by 3. So here we have that is 3. So WLX by 2, 1 minus 1 upon 3 beta square. And for reaction, we have that is WLX by 2, 1 minus 1 upon 2 beta. That is for shear. So these values you have to keep in mind for transfer of load from slab to beam. So now we will stop here only. Thank you.